So here we have the equation of the mass of a star, Alpha Centauri. It's our closest star, 2.1 light years away. And its mass increases as time goes on. You think of Big Bang cosmology, it's a massive thing, it's attracting more matter towards it, it's getting bigger and bigger. And so its mass is growing at 12% per year. And what's the question say? Where t is time in billions of years since the Big Bang. Okay, find the mass of Alpha Centauri after 5 billion years. So because time is in billions of years, that's when t is 5. And so we're going to find m of 5 is m0 times 1.12 to the power of 5. Now this question here, our answer is going to be in terms of the initial mass. We don't know what the initial mass is, but that's okay, we can still answer these questions. This is 1.76. Okay, so what that means is after 5 billion years, it is 1.76 times larger than it was when it was first formed. Okay, so it's increased by a factor of 1.76. Very good. Using logarithms, find how many years it takes for the mass of Alpha Centauri to double. Okay, so the mass is m0 times 1.12 to the power of t, and we want to find when the mass doubles. So that means when it's 2 times its original amount. So you can see, even though we don't know how heavy it was initially, we can still do all of these calculations. Because look at this here, we're saying, when is it double what it was initially? Well, m0, we can divide both sides by m0, it's going to cancel. So on both sides as a product, it can cancel. So, and what are we left with? This equation, 1.12 to the power of t equals 2. We can solve that using logarithms. We're going to log both sides, bring the power down, and then divide both sides by log 1.12. And then let's round to a few figures to answer in the context of the question. 6.12. Okay, here's a number. Billion years. Alright, because in this example, time is in billions of years. So whatever its mass was initially, it takes 6.12 billion years for it to double in mass. Okay. On to the next one. We have the pressure of Earth's atmosphere decreases the higher you go. So the further away you get from the surface of the Earth, the lower the pressure. The pressure at sea level is 1,013 hectopascals, and it decreases by 12% for every 1,000 meters you go up. So you can think how they've generated this equation. All right, they've said the pressure of 0, when the height is 0, is 1,013. And then you would multiply that by 1 plus or minus the growth of rate or decay. And it's going down 12%, which is 0.12. So 1 takes 0.12 is 0.88. So the power of h, where h is the height above sea level. So that's how they've generated this equation. Part A, find the atmospheric pressure at the top of the Empire State Building. So when the height is 381 meters. Now be careful here, because it says very specifically, it decreases by 12% for every 1,000 meters, okay? So that means P of 1 is going to be the height at 1,000 meters. Okay, P of 2 would be the pressure at 2,000 meters. So if we want to know the height, the pressure at 381 meters, that's going to be 0.381 thousand meters is 381 meters. So 0.88 to the power of 0.381. Let's crunch that. $964.8. Round to pretty significant figures. 965 has hectopascals HPA. It's the other way, it's capital P. Okay, hectopascals being the measure of pressure. Part B. The atmospheric pressure at the top of Mount Everest is 337 hectopascals. So you've seen the footage at Mount Everest, they need their oxygen mask up there, the oxygen's too thin. The question is, using logarithms, find the height of Mount Everest. So what's happening here is we have the pressure equation is equal to 337 hectopascals at the top of Mount Everest. It wants us to solve this equation. Alright, so this is the pressure, and at the top of Mount Everest it's 337, and that's not T, our variable is not T, our variable is H, where H is in thousands of meters. Okay, so let's solve for H. First thing we want to do, I've said, we want to get the exponential part by itself. When we're solving this logarithmic equation, we want to get the exponential part by itself. So let's move this 1013 over. We're going to have 0.88 to the power of H is, I'm just going to leave it like this for now. I'm not even going to calculate it until the very last step. Okay? That can save a bit of time if you can do that. Then what we'll do is we will log both sides. That power is going to come out the front. Might just do that in this step straight away. Save a bit of time. And then we will divide both sides by log 0.88. Okay, now this is probably a good time to emphasize to you guys. This does not simplify to one logarithm. Okay, so just by example, if we have log 2 on log 5, it does not simplify to log of 2 on 5. Okay, remember it's a function, so we need to keep them as separate logarithms. So that would not be correct. So this is our answer in exact form. All right, but it doesn't really answer the question. If someone says, how high is Mount Everest? You go, oh, it's log 337 on 1013 on top of log 0.88. Blah, blah. You know, unless they're a calculator, it doesn't make much sense. So let's calculate this here. So we're going to have log 337, log 337 on 1013. And what I'm also going to do, I'm going to treat it as two separate entities. So I'm going to type this in. This is what I'm typing in my calculator. I'm typing this in, and then I'm going to type in the divide button, and then I'm going to type in this. I'm not going to express it as two fractions because sometimes it can be a little bit risky, you can get it around the wrong way. So divided by log 0.88. And then you're very clear what's at the top and what's at the bottom of the fraction. Let's do that. I've got 8.609 or 8.61, three significant figures. Okay, and our answer, remember we've got pressure in hectopascals, height in thousands of meters. So it's 8.61 thousand meters or 8.61 kilometers you can think about. So that's our answer to part B. That's the power of logarithms. Okay, so that's enough to get into F. Let's do some. Thank you.